if I just pass the factor of I and h bar to the other side of the equation.
You agreed it was positive, right?
No, I just check. I don't really know this. What I know is this.
Okay.
I don't know the Schrodinger equation. I'm not kidding. I don't know. I know this thing. I could never memorize the Schrodinger equation. Okay, so for simplicity also, let's set from the start. Because I'm going to forget factors everywhere at some point. So, all right. They set units in which everything has dimension of mass to some power. All right. So whenever we write like any quantity, this is a symbol to say the dimension of this equals to some number. We actually mean that this has dimensions of. We should actually write like mass to some power, but it's not the case that people usually do. People just simplify, write just a number. Right? Why is there a camera on here? You guys recording? Okay. Okay. All right. So first thing to notice is, and this thing was the usual thing, right? Okay. This is not the relativistic expression we have for energy that we put in here, right? So if you want to correct this, if you want to give it a try, so the issue is, for very small things, we already know the quantum mechanics should dictate the rules of the game, not classical mechanics anymore. But also, we learned in the beginning of the 20th century that whenever things move too fast, we should not use non-relativistic physics, right? Like Galilean transformation laws. We should use special relativity, which is based on Lorentz transformation. Oh my gosh, I was about to say Minkowski, but it's Lorentz. So the first guess will be to try and write, instead of this, some type of operator that follows the relativistic energy, which is, do you guys remember the formula for relativistic energy in terms of?
I nominate Inch.
Say that again? Wait, E squared equals what?
M squared C is to 4.
C 4
plus P squared C squared. But since C equal to 1, we just get M squared plus P squared.
Great, thank you. Okay, let me also. Okay, but first thing you notice from here to here is that here the factor of energy appears by itself. Right? Hamiltonian is basically energy for regular system. For most of the system, we can generalize our notion of energy if we want to, by saying that the Hamiltonian of a classical system defines the energy. That's it, which not necessarily is the case.
Do you know what's also we said Hamiltonian is just an object which tells the system how to evolve in time.
Okay, so people sometimes like to say that energy is the thing that dictates energy evolution, right?
Yeah.
It's the generator of translations in time. So in quantum mechanics that's evident, but also there is some kind of statements that we can do this in classical mechanics as well. So it's fair to say that the Hamiltonian will be related to energy, right? So how do you do now? What should we do here? Should we you know, this has only one power of energy. This has.
I have a suggestion. I think because, well,
What do you think people did in the first place?
well, you have the energy. The professor gave you the energy is squared, and it's equal to m squared plus p squared. But we see in the Schrödinger equation, we have just h. So if we take a square root of both sides, we can just get e equals the square root of m squared plus p squared. And then maybe we can promote things to operators, and everything will be okay. Maybe I'm just maybe I was
Like this, right? But there is this issue first of a plus or minus. If you want to, we can say that we only have the positive roots, and since it's easier, I mean, whenever we don't know how operators act, this will be an operator here, right? We'll have to expand, make a Taylor expansion, and we can do this considering that P is not just for the sake of later on we're gonna call this vector, but because at some point I'm gonna use P without the vector, without the arrow on top to represent the 4 vector. This is just the 3 vector, right? Okay. So what we can do is just hold the factor of m out. And do a Taylor expansion just like we did with Chatterjee. You guys remember that? Yeah. I don't remember the names of this. Is this a fine structure? Hyperfine? I don't know. Yeah, one of those corrections. One of those corrections. But the problem is, we know that we have powers. If you Taylor expand this, we have several powers of P, right? Every other term. The next term will have always 2 more powers than the first. Yeah.